Hello, everyone. This is Group 9. Today, we're gonna produce an optimal algorithm for map task scheduling in MapReduce. My name is Yun Cheng, and this is Rupa and Jaya. So before we start, I gotta first talk about the MapReduce. So for MapReduce, is when a data processing request under the MapReduce framework, which is a job consists of two types of tasks, map and reduce. A map task reads one data chunk and processes it to produce intermediate results, which are key value pairs. And then reduce tasks fetch the intermediate results and carry out further computations to produce the final result. While we are assigning map tasks, a critical consideration is to place map tasks on or close to machines that store the input data chunks. And the problem here is a data locality. Locality refers to the fraction of tasks that's run on local machines. Improving locality can reduce the processing time of map tasks and the network traffic load. Next page. We have a figure here. So the red one represents the busy, the machine is busy, and the green one represents the machine is idle. So when we were sending all tasks to local machines, that may lead to an uneven distribution of tasks among machines. So in other words, so some machines may be heavily congested while others may be idle. Therefore, we need to find the balance between the data locality and the load balancing in MapReduce. Next page. And so we propose a new queuing architecture and a map task scheduling algorithm by join the shortest query policy together with MaxWeight policy. So there are many scheduling algorithms commonly used in practice. The first one we're going to introduce is a FIFO scheduler. So for FIFO scheduler, when a machine is ready to run a new task, the scheduler first selects a job according to a priority list, which is a FIFO query by default. And then it schedules the map task in the job with the data closest to the machine. And there are also an alternative scheduler available, which is called fire scheduler. So instead of using a FIFO query as a priority list, the naive file sharing algorithm uses a certain form of fairness as a priority. And in here, the locality optimization is the same. So the Hadoop cluster shared across multiple jobs. So for our system model, the paper assumed that there are a random number of map tasks. Tasks can be classified in here as types. And also we assume assume that each data chunk is replicated and placed at 3 different machines in here, A, B, C. So each task is associated with 3 local machines. And at each machine, the service times of tasks follow geometric distribution, and the tasks are non-primitive. And we assume the average service time of local tasks is less than the remote tasks. We propose a new querying architecture with one local query for each machine, storing local text associated with the machines and a common query for all machines. So based on this new querying architecture, we propose a 2-stage scheduling algorithm. So there are 2 steps. The first step is we call it routing, and we use the join the shortest querying policy. And the second is a scheduling, and we use the MaxWeight policy. Next, Rupa gonna introduce the details about those two algorithms.
Okay, thank you, Yunchen. So now that Yunchen has explained the background and the setting, let's get into the details of the algorithm. So we have a master, one single master, and there are M machines. So the master has maintains a queue for each of the machines. So each of the queue basically has the task that has to be handled by that machine. This is based on the locality. If the data for the task is stored in a particular machine, and then so the data basically it might be queued in that particular machine's respective queue. And there is also a common queue for all the machines that the master maintains. So altogether, there is basically m plus one queues. And we need to remember that the tasks are non-preemptive. That basically means that if a machine starts working on a task, it will complete it, even if regardless of the priority of the new arrived task, it cannot be the existing task cannot be removed. And we need to look at the parameters alpha and gamma before we get into the algorithm. So alpha is the service rate or the probability that a task would be successful at a local machine, and gamma is the similar parameter for the remote task. So let's get into the algorithm. As Yuncheng mentioned, the algorithm is performed in two parts: routing and scheduling. So first we'll look at the routing, and then we'll get into the scheduling. Before we look into the routing, let's take a real world example. Let's say a customer or a user wants to buy one item from two identical shops. One of them is closer and one of them is farther. So if his goal is to save time, then which one would he choose?
The
The closer
closer
one.
one.
Closer one? Exactly. Yeah. So he chooses the closer one. That's exactly what the algorithm does. As the first part of the algorithm, the routing process, the master chooses the shortest queue. It's basically called shortest queue routing. So let's see. As soon as a task arrives at the master looks at the task and then figures out which are the machines containing the data related to the task. And because there are three replicas, so there will be three machines. So these are the queues related to the machines that the master maintains, and there is also the common queue. So now we see that all these queues are filled to different extents. So we see that Q2 is the least full, or I mean, it is like it is least occupied. So here, based on our previous example, which one should the master choose and queue the task to? Which queue?
Q2 in here.
Exactly. Yeah. So it should choose Q2 because it has least number of tasks. And so the next question: what happens if there is a tie? If task two and task three have the same number of tasks queued up, then what would happen? So as per the paper, the tie is broken randomly. Okay. Now that we have understood how the queues are filled up by the master, let's get into the scheduling part of it. All this we already discussed. The scheduling algorithm is called MaxWeight scheduling. So once a machine starts a task, it has to finish it. So once it finishes a task, and the state of the machine is will become idle. Once a machine becomes idle, the machine has two options: either it can pick a task from the local queue, or it can service a remote task. That's not the job of the machine to decide which one it has to do, but the master will actually schedule. So the master uses this equation to decide whether a machine should service a local task or a remote task. So here we see that alpha is the service rate and this is the queue length. So multiplied together gives us the local queue weight. And gamma is the service rate for the remote task, and this is the common queue length, and multiplied together gives us the common queue weight. So now whichever has the higher weight, that's the task that has to be serviced first. If the local task, like for example, at this point, alpha and QMT is higher than the other one, a master will actually say choose the machine to service a local task. That's that's the main idea behind the MaxWeight scheduling. And I will pass on this to Jayashree.
Thank you, Rupak. Next, the paper proves that the algorithm is throughput optimal. So let's first discuss on why do we need it. Throughput is nothing but to make sure that the system schedules the tasks such that it maximizes the number of completed tasks within a given time period. That is our main goal. And in order to prove that, firstly, we need to identify the outer bound of the capacity region, which is nothing but a set of arrival rates, such that it satisfies certain conditions, such as the average arrivals allocated to the machine in one time slot must be able to served within one time slot. So here is the equation of the outer bound in terms of the arrival rates, and the necessary condition less than or equals to corresponds to the necessary constraint that we discussed. And then the paper proves that the algorithm lies within the defined outer bound, making it throughput optimal. Without going deep into the mathematical proof, I will state a few highlights of the proof. The paper uses squared of the L2 norms of the Q length as the function which is expressed in this first equation. And then using expectation of difference of the squared L2 norms, the second equations, it proved that the algorithm lies within the outer bound. The outer bounds were defined in the next equation. So hence it is proved that our algorithm is throughput optimal. Now let's observe the simulation results. Here, in the paper, the throughput performance of the proposed algorithm is compared with the naive fair share algorithm. So in the first figure, we keep track of the number of concurrent jobs in the system with respect to the each time slots in order to observe the stability. So here stability is nothing but a bound until which a scheduler can handle the tasks. Now in this figure, we can observe that with an increase in the time slot, our algorithm is almost constant, while the naive-Fair algorithm is increasing continuously. So in the next graph, we'll exactly get the details of until when the algorithm is stable or not, with respect to the total arrival rates and the average number of concurrent jobs. So here we can observe like until in the smaller arrival rates, both the algorithms perform really well. But with increase in the arrival rates, the naive-Fair algorithm breakdowns at around 390, while the proposed algorithm handle until 670. So this clearly shows that our algorithm is more stable than the naive-Fair algorithm, which concludes that the throughput of our proposed algorithm is increased by more than 80% compared to the other. So now let's compare the other performance metrics, which are the job and the task delay with respect to the total arrival rates. So first, what are these delays? So the job delay refers to the delay between the time the job is submitted to the cluster and the time when it's actually running. This could be mostly caused due to factors like network congestion or the scheduling issues. While the task delay refers to the delay between the time when the task in the MapReduce job is scheduled to run and the time when it's actually running. So this is could be caused due to data locality or the resource availability. So these are the two important metrics that we are comparing between our algorithms. So in the first graph, we can observe that when we compared the total arrival rates with average job delay, it performed really well for the smaller arrival rates. Actually, both delays, both job and task delays, performed really well for the small arrival rates. While when it crosses a threshold, like for an Fisher algorithm at around 350, there has been a breakdown and it couldn't handle the job delay. Job delay just goes on increase and increase and increase. The same goes with the task delay also. So this could conclude that our algorithms perform well at the small arrival rates, but in general, our proposed algorithm is performed twice as good as the Nair-Fisher algorithm in terms that it is roughly it half the job delays, the average job and the task delays, it reduces to half. So this concludes our proposed algorithm and the results. Next, Rupak will discuss about the improvements and the weaknesses.
Thank you, Jayashree. So now that we have discussed whatever is presented in the paper and related work and the background and setting, uh, let's look at our observation and comments. First, the algorithm assumes that there is only one master, so one master could be the single point of failure. And in a real world setting, a master is actually an entity. It's not just a node. So there could be multiple masters all communicating with each other, acting as one single master. In that case, so in this figure, if you look at it, we have two masters, and then there are three machines shown, and each of them is connected to each of the master, and the masters are also connected to each other. And in that case, so there are a lot of complexities involved here: the master election, and then the consensus between the masters, and the delay from master, each of the master to the machines could be different, depending on the location of the masters. So all these factors will actually influence the throughput and how the algorithm changes. So this part is not captured in the algorithm. Another aspect of the algorithm is the algorithm assumes that the service rates of each of the machines is equal, which is a parameter called alpha, but then the machines could be of different capacity. One machine could have more processing power, or probably the machine could be closer to the master, and in that case, it will perform faster. So all these factors will actually come in. These are the details that are not covered as part of the research work in the paper. And if we look at the network congestion, so for example, the masters maintain a queue for the machine 3, and the machine 3 has the least amount of a task queued up. But then there is a congestion towards the machine 3, and which is not actually reachable currently. If a task reaches the masters, and then they see that the queue is the least for the machine 3, then they might actually queue up for the machine 3, but then they might never be able to send the task to machine 3 to complete it. So these kind of scenarios are not taken care in the work. And we already talked about the tie breaking. So if two nodes, for example, here machine 1 and machine 2, the queues are exactly of same length, in that case, we should not be breaking the tie randomly, but then as an improvement, what we can do is, depending on the node processing power or the closeness to the masters or the combination of both, or maybe there are several multiple factors, all of them could be taken into account, and the tie can be broken. So moving on to some other weakness, the paper takes the real world data, but then it evaluates them in a simulated environment. But in general, that's not the case. In a real world scenario, there could be multiple variables which might be affecting the throughput. Hence, the evaluation also could have been done in a real world setup, and we need more data regarding evaluation on the real world scenarios. Also, the paper assumes that there are only 3 replicas of a particular task. So what happens if there are 4 or more number of copies? The paper doesn't discuss those aspects. Then moving on, the paper doesn't actually compare its results with any other state-of-art schedulers like capacity scheduler. And also the paper is actually discussing and focusing only on MapReduce tasks. That's fine. But what is its applicability on other types of distributed systems like distributed databases or distributed graph processing systems? And so these are some of the improvements that there can be work done in these areas, and then they can be captured, so that it will be the algorithm's applicability can be known for a wide range of applications. Moving on, so we kind of discussed the improvements that can be done. So the alphas can be tuned as per the machine capabilities, and then a number of replicas can be increased and then seen. And the tie breaking we already discussed. So compare with other state of art algorithms like so FIFO. So the paper doesn't actually discuss about the FIFO because they already discussed about the knife fair share scheduler, but then there are many other algorithms which are already existing and are used in the data centers, and the paper can actually do an evaluation on them and also investigate the applicability on different types of systems. A comparison with Hadoop delay scheduler. So this paper assumes the evaluation of the paper is based on the assumption that the tasks are non-preemptive. So the tasks should not be preempted. What that means is if a machine starts running a task, it should take it to completion. But then if a high priority task comes in, maybe it can be preempted and it might help in the throughput. That's what the Hadoop delay scheduler takes into account. But the goal of this paper is just to increase the throughput, um, irrespective of any other constraint or any other limitation. So the paper does a good job in that aspect, but then it doesn't take into account things like data size. So for example, in Hadoop delay scheduler, if a task takes more time than any other task, that's basically called data skew in the data center terminology. So Hadoop introduced a delay for those kind of scenarios, and then it handles that. But the current paper doesn't take into account these kind of things. Having said that, so in this simplistic setup, this algorithm performed much better than the knife fair share scheduler, as shown in the simulation results by Jayashree. So to conclude, this was an algorithm which was the very first talking about non-preemptive tasks and scheduling on those tasks, and then employ the data locality to gain the optimal throughput. And it also goes on to prove that how optimality can be obtained based on the data locality. It actually provided a good start for many other research work that would happen later on, taking on this platform and improve upon this. So overall, yeah, this algorithm was a good start. That concludes our presentation. Thank you.